This is a short video about Wilson's theorem in section 2.1.3 of Stein's number theory book. And what is Wilson's theorem here? And what it is, it's sort of like a way to test if an integer is prime. And it's kind of fascinating because it's as old as the 1770s. And so what's the statement of the theorem? An integer p is prime if and only if p minus 1 factorial is equivalent to negative 1 mod p. So recall also to negative 1 mod p, that's the same thing as p minus 1. And so if you scroll down, I did say it was a way, that is a characterization of prime numbers, right? And again, as old as the 1770s. But what you could guess, though, is that, or what you might notice, computing factorials get out of hand in a hurry. So like, for instance, if p is 17, this would be 16 factorial. 16 is a relatively small number. 16 factorial is ridiculous. That's gigantic. So factorials get big really fast. So it's an interesting problem to try to calculate, is a particular number prime or not? Wilson's theorem would not be the tool to use to do that. But at any rate, it's still fascinating that it's as old as the 1770s. So that's what we're going to try to prove in this video. And as the book jokes, it's literally the least efficient way to test if a number is prime. But it's still kind of neat. So what's the proof? It's an if and only if, and we're going to assume that p is a number that's bigger than 2. And so since it's an if and only if, let's assume the first part. Let's assume p is prime, and we'll try to prove that p minus 1 factorial is equivalent to negative 1 mod p. So if you took an element that's in the set from 1 up to p minus 1, it could be any one of those, then what do we know? Well, I know that each one of these numbers is relatively prime to p, because p is prime. So p is relatively prime to all the numbers that are less than or equal to it. So then what do we know? Well, we know that linear equations, this linear equation, ax is congruent to 1 mod p, it has a unique solution exactly when a is relatively prime to p. And what we just said is, well, that works for all these a's. So in particular, I know that this should always have a unique solution, we'll call it a prime, and that a prime should reside in this set too. Now, there's the idea that we want to do is, I would like to pair each a off with its inverse a prime. Because what I'm going to do is, in Wilson's theorem, what am I doing? Well, I am multiplying all the numbers less than or equal to p minus 1. So what I'd like to do is, just when I multiply, I'd like to group the inverses next to each other. And to give you maybe a more concrete idea of what I mean, if I scroll down a little bit, let's think about mod 17 here. Then if I multiply 2 through 15, what I'd like to do is I'd like to group each of these numbers 2 through 15 with its inverse. So instead of this product here, I just want to put some parentheses around. I'm going to group 2 with 9. 2 with 9 is 18, but then that's congruent to 1 mod 17, right? And so what I'm saying is, again, in parentheses, I've grouped each number with its inverse so that I see that product, it's 1 mod 17. Now there's something that you should be careful about here. So that's the basic idea of what I want to do again. I want to take each element a from 1 to p minus 1. I know it has an inverse, so I just want to group it with its inverse when I multiply all of these elements here. The thing you should be worried about is, what if an element is its own inverse? So like, for example, in Z3 or Z mod 3Z, 2 times 2 is 4, but that's 1 mod 3. So 2 is its own inverse. So what about the case that an element a is its own inverse here? Well, necessarily then that says that a squared is congruent to 1 mod p. From the last video, we know that that's also telling us that the order of a is at most 2. Now when I say at most 2, maybe you're like, why not exactly 2? Well, it's possible a is the identity 1, in which case that has order 1. But what we're going to show is we're going to conclude that, well, if a has order at most 2, in fact, a has to be either 1 or p minus 1. And how we conclude that, since a squared is congruent to 1 mod p, maybe we'll write out what the definition of that means. I should subtract the 1 to the other side and recall that this equivalence relation here tells us that p divides a squared minus 1. Now factor a squared minus 1, and you know that p is prime when p divides a product. So maybe what I could highlight here, p divides this product, you know that p has to divide at least one of the factors. In other words, p divides a minus 1, or p divides a plus 1. And now if you think about it, right, if p divides a minus 1, what would that look like? That would tell me p divides a minus 1. In that case, though, a minus 1, if a is in 1 to p minus 1, how is it possible that p divides a minus 1? So in particular there, that tells me that in that case, that a itself has to be 1, since the only way that could be true is p divides 0. So again, if a is a number that's strictly less than or equal to p minus 1, then the only way this could be true is if a minus 1 is 0. So in particular, it's only possible if a is 1, or on the other hand, if p divides a plus 1 again, in that case, what we should be able to conclude is that that would mean that a has to be equal to p minus 1. And so if I plug in p minus 1 for that a, I hope that you see that the 1's would cancel. And that's the only possibility that we'd have again. So in particular, what was I worried about? In this example that we did down here, it was nice because all the factors in the product were able to be paired with its inverse. And we were potentially worried about, what if you had a situation like in Z3 where an element like 2 is its own inverse? Well, that's okay in this case because I know what it would have to be. I know how to handle those numbers now. So what can I say for sure? I can say for sure that when I multiply 2 up through p minus 2 in this case, I can pair each of these elements 2 through p minus 2 with their inverse. So maybe to be a little bit more clear, we've just justified that everybody in this set has an inverse that's not themselves. So in other words, none of these numbers that I've highlighted in green here can be its own inverse. The only possible numbers that are its own inverse are 1 and p minus 1. So at this point in the game, what do I know? I know that when I multiply these numbers together, it's possible for me to group them with their inverse, just like we're doing down here in the pink, so that this product is equivalent to 1 mod p. And now the last thing that you would do is you would multiply both sides of this by p minus 1, so that when you simplify, this is p minus 1 factorial, and just recall that p minus 1 is congruent to negative 1 mod p. And that proves one direction of Wilson's theorem. So since this is a biconditionalist if and only if, now we've got to do the other direction. So the next thing that we'll do, I'll pick a different color too, that sounds fun. Let's assume that p minus 1 factorial is congruent to negative 1 mod p. So we want to show that p has to be a prime. So let's do a proof by contradiction. So suppose p is not prime. That means p is at least 4 and it's composite. So p is composite, it's got factors. In particular, we know that each composite number is a product of primes. So why don't we let L be a prime divisor of p? So prime is one of L is one of p's prime factors. Well, if L is a factor of p, then certainly L is less than p. So if you think about p minus 1 factorial, L ought to show up in that product p minus 1 factorial, which of course means that L divides that product p minus 1 factorial. I hope you see that. L is one of these things in that product. It's one of the factors. But then what else do I know by assumption? So I have assumed that p minus 1 factorial is congruent to negative 1 mod p. Think of the definition of that. That says that I think sometimes people call it the modulus, should divide this minus this. Wait a minute, that's p minus 1 factorial plus 1. So far what I want you to think about is we know that L divides p, since L is one of p's prime factors, but by this hypothesis here, that says L also has to divide p minus 1 factorial plus 1. Actually, hold on one second. So more importantly, where the contradiction is going to come from, sorry about that. L divides p minus 1 factorial, but L also divides 1 more than that. So think about it. There can't be a prime that divides a particular number, but then also just 1 more than that number. That cannot happen. And so that is our contradiction. So again, we've got a contradiction because L, it's not possible that L can divide A and also a number A plus 1. It's not possible that L divides p minus 1 factorial and also that L divides 1 more than that.